calculate
Higher.
the area of a triangle from its side lengths. And the area is equal with the square root by p times p minus a times p minus b times p minus c, where p is the semi-perimeter of the triangle, so it's equals with a plus b plus c divided by 2. Heron of Alexandria was a Greek mathematician who was active in his native city of Alexandria. He is considered the greatest experimenter of antiquity, and his work was representative of the Hellenistic scientific tradition. We can demonstrate his formula using the Pythagorean theorem in two triangles in BPC and APC. And we get two equations, and we're solving the equations for x. And we got x, it's equals with a squared plus c squared minus b squared, all divided by 2c. Now we substitute the third relation in the first one, and you get we get h squared equals with a squared minus a squared plus c squared minus b squared all square divided by 4c squared. And we do square difference, and we get this. H is equal with 2 square root by p times p minus b times p minus a times p minus c all divided by c. And when we substitute all this in the classic formula of the area, we get exactly the Heron's formula. For our triangle, the semi-perimeter equals with 127.5 meters, and the area is more or less than 1022.6 meters square, and this is bigger than 1000. And the result, the area can be built.
Donc l'aire du quadrilatère n'est pas constante, comme je disais précédemment. Elle varie soit selon l'angle, soit selon la diagonale du quadrilatère. Donc si on note, je vais faire un schéma. Donc x, c'est la variable aléatoire. Ça signifie que on peut bouger, donc ça peut changer. Et donc on a appliqué 2 fois la formule de Héron, c'est ce qu'elle a dit tout à l'heure. Et donc on a trouvé ceci, ce qu'on a additionné. Donc ensuite on a dérivé la fonction pour étudier ces variations, mais on n'a pas pu trouver le signe de la dérivée, donc on a décidé d'aller sur GeoGebra et on a tracé la fonction. Et ensuite, donc la fonction est représentée par la parabole. Et ensuite, on a pu trouver les points qui correspondaient à 1000. Et lorsque c'est au-dessus du 1000, donc l'espèce de petite courbe, ça veut dire que le terrain est constructible. Donc on a cherché les valeurs de A et de C. Et donc on voit que c'est environ 47,93. Et là, on peut voir que c'est 52,41. Donc on est proche de ce qu'on a vu tout à l'heure, mais on ne pourra jamais trouver une valeur qui restera. Ça sera toujours mobile.
To calculate the area of a quadrangle, we use the Schneider formula, which is that the area of a quadrangle equals with square root by s
minus A times S minus B times S minus C times S minus D minus ABCD times cosinus square by alpha plus gamma divided by 2. The area of the first quadrangle we use the Birch-Schneider formula, and we found out that the semi-perimeter is 67.5 meters. If the alpha plus gamma equals with 180 degrees, the value of the cosinus is 0. So the maximum area is bigger than 1,000 meters square. So in this case, the area can be built, but it can take other values which are smaller than 1,000 meters square. For that one, we took a particular case in which the value of the angle is 90 degrees. So we calculate the area using the Pythagorean theorem in two triangles, BCD and BDE. So we are solving for x, and we found out that x is equal with 24.25 meters. And we calculate the height, and it's about more or less than 25.23 meters. So the area of the quadrangle is the area of BCE plus the area of ABE, and the area of BCE equals with 630.55 meters square, and the area of the ABE equals with 300 meters square. So the area of the first quadrangle is smaller than 1,000 meters square. So the area of the first quadrangle depends on the measure of the angle. So we can take different values.
Okay. For the second quadrangle, we do the same. We use the Birch-Schneider formula, and we calculate the semi-perimeter, which is 67.5 meters. We calculate the maximum area, and we see that is smaller than 1,000 meters square. So the area of this quadrangle can be built.